Okay, so let me remind you how we can solve the two-dimensional problems. And so in case of a two-dimensional problem, we can easily say that there are two coordinate systems, first of all. One is the global coordinate system. So in this case, x and y, x is horizontal and y is vertical. And the other one is the element coordinate system, ye and xe. Indeed, xe is in the axis of the member, in the axis of the element, okay, and ye is perpendicular to it. And xe makes an angle of phi with the global coordinate system x. So this is the angle that it makes. So basically, this means that we have to transform the coordinate system in one variable, variables in one coordinate system to the other. As a result, we have to make a coordinate transformation. And moreover, remember that in one-dimensional problems, we have only two members which are associated with each node. But in this case, we have two variables associated with each node. So in x and y coordinate system. Okay. As a result, we have the again, if you write the force equilibrium in element coordinate system, as you see, only x components contribute to the force. So in fact, the first row is associated with the x component of the force in node 1, at node 1. And the third row is associated with the force component in x direction associated with node 2. And the y component of the forces are not associated with the displacement because they are zero. In fact, we don't have any perpendicular force associated force displacement coupling in the perpendicular direction. So we have zeros in the second and third rows. So this is the enlarged version of the element stiffness matrix, which is written in the elemental coordinate system. In fact, remember that we have to transform it. Now, how we do the transformation? This is the point. So we do the transformation like this. So the element displacement can be transformed by rotating the values in the global coordinate system. Simply, it is geometry. So u1x cosine phi, if phi is the angle between the global and elemental coordinate system, so u1x this is the displacement in the global coordinate system, and u1y is the displacement value at node 1 in the global coordinate system. So u1x prime is u1x cosine phi multiplied by u1y sine phi. And identically, you can obtain the similar expression, not the same, but similar expression for the y coordinate system. As a result, we have this relationship. So RE multiplied by DE. RE is the rotation matrix. I will talk about it. DE is the displacement in the global coordinate system. So RE multiplied by DE will give us the displacement in the element coordinate system, D prime E. Now the point is this, then we have this rotation matrix. So remember that this is associated with the node 1, and you see this is the coefficients of u1x, u1y, right? It comes from here like this, and this is here, and this comes here, and this comes here, and then it will be the same for node 2. In fact, as a result, we obtain this rotation matrix. Simply, this rotation matrix has some properties. It is inverse is equal to its transpose. As a result, multiplication of the rotation matrix with its transpose will give us identity matrix. And of course, we can obtain the stiffness matrix of the element in global coordinates by doing such an operation. So this is the operation that we need to do, that we have to do. So first we write the stiffness in element coordinates, which we did for one-dimensional problem already. Then we have to multiply it with its transpose and with itself, with the rotation and with the transpose of the rotation matrix and with the rotation matrix. And then we obtain the stiffness matrix in global coordinate system. Okay, it will be much more clear when we begin to solve some problem. So we have already solved the problem, and let's go through it and try to solve it. So let me remind you the problem. Now we have a system of truss elements. Elements are numbered as 1 and 2. The node numbers are 1, 2, and 3. Now x is horizontal, x-axis is horizontal, and y-axis is vertical. The length of the distance between node 1 and node 3 is given as L, and node 2 and node 1 is given as L2. So we need to solve this problem. In fact, we are given a force of 10 acting at node 3. Okay, now what we need to do is to write the stiffness and rotation matrices. Okay. First, we will begin by writing the element stiffness. Now it is KPE. Let me enlarge it. I go to the window magnification and increase it, or let's change it as 150 maybe. Okay, this is better. Now K prime E is the function of element stiffness, KE, okay? And let me write it. Now for two-dimensional problem, my matrix has 4 members. This is 1, this is 0, this is -1, and this is 0. My second row is completely 0, because I don't have, there is no force displacement coupling in the y direction. Now my third row is -1, 0, 1, and 0. third row gives the relationship between the force at node 2 in x direction and displacements. And my last row is 0. Okay. I put a semicolon. I don't want to see it in the screen. It seems okay. I evaluate it. Now let me define the rotation matrix. I say that rotation. Now I will define the angle as phi. Again, I have four variables in each element. So two variables are associated with each node. So this is cosine phi, sine phi, it is 0, it is 0. Well, it is red because I put the square brackets in the wrong place. Now it's corrected, but now the brackets are not coupled. Let me delete it. That's okay. Now my second row is minus sine phi cosine phi okay. Then the rest is 0. Now I have the rotation associated with the node 2. Now it is 0, 0. Again, it is cosine phi, sine phi, and let's continue. It is 0, 0 of curly brackets. 0, 0 minus sine phi cosine phi. So this is the rotation. I will put a semicolon at the end of the line. It's okay. Now I want to write the element stiffness matrix in the global coordinate system, but certainly the element stiffness matrix is a function of the angle of the element and its stiffness. So this is transpose. This command, transpose command, takes the transpose of a matrix. So it is rotation matrix and the dot KPE KE. Now dot means that you can multiply these two arrays. So first I take the transpose of the rotation matrix. It's a 4x4 matrix. As a result, the transpose will be 4x4, and it will make a matrix multiplication. This dot means that it will make a matrix multiplication with KPE, and then rotation. Now, of course, this may give us some complicated expression. So let's see what it will give us. Okay, so this is my stiffness matrix in the global coordinate system. Now, let's go back to my slides and let's see the steps in the solution of the problem. Now I have two elements, right? K1 and K2. So for the K1, I have the element stiffness, area 1, Young modulus 1, and length 1. And since for this problem, area is constant, Young modulus is constant, and length of the element is constant, and K2 is equal to area E and square root L. So let me write the element stiffness matrices. For each member. Let's return back to Mathematica. First, with the first element, KE1. So KE1 is equal to KE. Now I need to write the angle. So phi is the angle, but Mathematica uses angles in units of radians. So I write P divided by 2 here. P is automatically defined. So you don't need to write the value of the then it is area or A multiplied by E divided by L. So let's say L in order to not to confuse it with some other, because it gives me a black here. So this basically means that E is associated with some function. So I write EL in order to define that, in order to make it different than the E. So it is elastic modulus or Young modulus. Okay, so this is KE1, and let's see what the value is, or just put a semicolon here and see it in a nice form, matrix form. KE1. You see? So it gives me this one, 1, minus 1, minus 1, and 0. Let's go back to the solution, whether check it with the solution of the problem. Yes. So 1, minus 1, minus 1, 1. This is associated with the node 1 and this is associated with the node 3. So that's okay. But I didn't see the coefficient. So this basically means that I made a mistake somewhere. Ah, well, here I made a mistake. I forgot to multiply it with the KE. Now it is okay. I reevaluate all the ones again step by step. Yes, now here it comes. Yes. So this is my KE1. Now I will copy this one. Now I will define the element stiffness matrix for matrix 2, for element 2. But this time, the length of the element is square root of L. Square root L multiplied by square root 2. Now I put square root 2 here. But of course, I have to modify it with the KE2. Again, I press Shift Enter. Well, the angle is not P divided by 2. Certainly, it is P divided by 4. It's 45 degrees. Huh? Okay, here it comes. Now, I have the element stiffness matrices and associated with each node. Now, I have all the values. Next step is to assemble these ones. Now, I have to write a gather and scatter matrix for this purpose. So first, I need to get I have to make it enlarged. Okay. Now the point is, as you see in this matrix, these two lines, the first two rows are associated with node 2, node 1, and the last two rows are associated with node 1. So I need to enlarge these elemental stiffness matrices. So what I'm going to do is, first, I will check something. In fact, I will decompose the matrix. Now I have two matrices, right? KE1. This is how I'm going to look at the indices. So 1, 1, you see it is 0. And 2, 2 is not 0. Area multiplied by elasticity divided by square root of L. So I will get the sub matrices of each one. So I have here 4 sub matrices which are 2 by 2, but let's do it like this. I will create sub matrices. I put 2 semicolons here, 1 to 2, and again 1 to 2. Okay. Now I will generate matrices 2 by 2 sub matrices, and I will add 2 zeros here in order to enlarge it. and I will write join here. And see how it will join these two ones. And then let's assign a dummy variable, and I call it dummy. And I will visualize it in matrix form in order to see how this command, this join command, combines these two matrices. Not join, join. Okay. So it adds to the column. It's also okay, no problem. Now I can add here and another one. So it is 1 to 2, right? Now I have 3 to 4. I just get the submatrices of the KE1. There seems to be a problem. So let me copy it. I made a mistake here. So the submatrix that I get is, I just need to change the number of rows. So it is number 3, row number 3 to 4. In fact, when you write it like this, the first index shows the row numbers. So basically from rows 1 to 2. And then I join it from row numbers from 3 to 4 and the column numbers from 1 to 2. Okay, now it's okay. So this is my dummy matrix. Now, of course, let's say that this is dummy 1. Now I will do the same thing for the last 2 columns because it makes column wise. This join command creates a column wise operation. Again, from row number from 1 to 2, the column number from 3 to 4, and I modify it from 3 to 4. That's okay. Now I have the dummy 3. Dummy 3 will be zeros. So I have 2 by 4 zero matrix. But sorry, 4 by 2 zero matrix. So this is my dummy 3. Again, I put a semicolon here. I will remove this line from here. Now let's evaluate it. That's okay. Now I have the dummy matrices. Now I will join these dummy matrices in order to So it is transpose of dummy 1 now KE global or global coordinates KG1, let's say that this is the first variable. So KG1 is, K is for the stiffness, G is for the global, and E1 is for the element 1. And now I will join and check it, transpose of dummy 1 with the transpose of dummy 3. And let's see how it works. It didn't work. Why? Let me check it, because I need a 6 elements. Sorry, I need 6 rows in dummy 3, and this is why it didn't. It was not able to join. So I will add 2 more rows to the dummy 3. Now it should be okay. Yes, now it's okay. Now let me add the last line. So transpose of dummy 2 what's the problem? Well, it's here, it's wrong. It's not 4 by 4, it's 3 by 4. This has to be 3. So yes, correct it. Now it should be okay. Yes, it seems to be okay. But certainly we need to take the transpose because all the matrices are transposed. Now it's okay. Yes. So we have the KGE1. So this is the x coordinates. Certainly the first element has a 90 degree, makes it a 90 degree angle. As a result, it is x variable of the element 1 is y variable in the global system, and it is the same for the node 3, and as you see, it is symmetric. Now we will do the same thing for the node 2. Again, I copy all these lines, but the point here is now something different. So remember that element 2, so let's go back to our slide. Yes, it's here. So element 2 only has nodes 2 and node 3. Therefore, first 2 columns has to be 0 in this case. Now, what I will do is this, I will just copy these zeros matrix. And put it here. Okay, and this is KE2. So node 1 of the element 1 is associated with node 2, and node 3 is associated with node 3, right? Okay, so again, we do the same thing for the dummy 2. And we have the dummy 3 here. Again, let's evaluate it. It seems to be okay. Now I will copy these lines from here and form the element stiffness matrix in global coordinates. Now the point is this. Again, I will just take these lines from here. Okay. And let's check it. Yes. Now, okay, so my matrices in global coordinates are now defined. So okay. Now let's continue forming the global stiffness matrix. Therefore, what I need to do is sum up these two matrices, KGE1 plus KGE2. These are my global, this is my global stiffness matrix. Now I have this global stiffness matrix, which is 6 by 6. So let's see it. Okay, so this is my global stiffness matrix, Kg. That's okay. Now I can solve the stiffness matrices, but remember that in the first two nodes, the displacements are already defined. And so this submatrix is my free submatrix. I will decompose the submatrices now. Okay, now So certainly what we are going to do is first we will generate the submatrices. So in fact, the problem is we need to not the problem, but let's create the free nodes and the matrices, submatrices associated with the free nodes. So remember that we have only node 3 is free, and as a result, this is the submatrix for the free nodes, and this is the fifth and sixth rows and fifth and sixth columns. So KFF is equal to KG five to six, and it is 5 to 6. So this is KFF. I put a semicolon here. KEE is essential to essential is KG 1 to 4 to 1 to 4, and KEF is, so essential to free coupling is KG 1 to 4 to 5 to 6. Since KEF transpose, as you see, this is equal to the transpose of this one, so the global stiffness matrix is symmetric, and as a result we only need to keep these values in the memory. Let me evaluate them. KFF, I just want to see them in matrix form. KEE, and KEF. Okay, so these are my matrices. So this is KFF. This is my KEE, and this is my KEF. So coupling between the essential and free nodes, which couples the essential and free node. This is my submatrix. So I define my submatrices. Now the point is this: I want to calculate the nodal values. First, these are my displacements. This is my external loads, and this is my reaction forces. Now I have this system of equations, so remember that. And I already decoupled the displacements. In fact, let's write the DE and DF. I don't need to write the EF, KF is okay, KEF is already defined. So I need to define DE here, this one, because these are known and these are 0. I need to define FF. Now let me define the displacements at essential nodes. They are all 0. That's okay. And forces at free nodes. I have 10 and 0. Okay, now they are defined. Now let's go back to my slides again. Now first step is to calculate the displacements at free nodes, okay, U3x and U3y. Certainly it is like this. I have the key EF transpose multiplied by DE. These are the forces generated at so they are 0, doesn't matter. I put everything to the other side of the equation. That's also okay. Now these are the forces coming to the node 3 in x and y direction, either through the displacements at node 2 and node 3 or through the external forces. Now I will multiply it with the inverse of KF. KFF, okay? Free coupling. And this is a matrix vector multiplication. As a result, I put FF. So here, let me write that instead of putting 10, I will write F3x. So I put a variable. Sorry, yes, F3x. As you see, these are my nodal values at the essential nodes. You see, they are the function of length, L, area, and external force applied to the node 3 at x in x direction. Okay, now I find the displacement df. It's okay. Now I need to find the reaction forces. So how can I calculate the reaction forces? Now, reaction forces are equal to KE multiplied by DE plus KEF multiplied by DF. Reaction forces at essential nodes. Now I write matrix form here. RE. And these are the reaction forces as a function of external load F3x, area, Young modulus, and length. Of course, I can calculate it for arbitrary angle without defining, without any definition. Anyway, so let's do something else. Or let's stop here, that's better maybe.